sine t cosine t. Okay, well I've multiplied this out and used that rule that I squared is -1, and I've gotten this. Well, I wonder if anyone recognizes this real piece here. If you know your trig identities, that's the angle addition formula for cosine. So this is cosine of t plus s plus I times t plus s. So that's why if you really multiply up here at the top, multiply the expressions on the right, you really do get this expression on the left. Because as I said, the definition of cosine t plus s plus I sine t plus s, that's e to the I t plus s. So that might help you accept this Euler formula, or it might be a good explanation for you to help a student understand why we like this Euler formula, why it makes sense to us. So now I want to just practice a little bit with exponential notation by inviting you to think about, I've got two runners around this circle. So now this circle has turned into a big track that I've set up. Maybe I took a rope and placed it at O and ran it around here and made a track there. And I've got one person at P here, but I've got another person at Q who's going twice as fast. So here, at the instant that I'm showing, this angle, POF, I'm going to double that angle to get QOF, okay? So this Q is the fast runner. Now in a minute we're going to see a video of this, but I want to encourage you to experiment with GeoGebra, because you really can just type exp2it into GeoGebra to create the point Q. When I typed that, I'd already set up the variable t with a slider so that it knew that t was going to be a number between 0 and 2 pi, which is the number for all the way around the circle. And then I created segment PQ, and then I gave GeoGebra the instruction to follow the traces, to show the traces of PQ. So at a different instance in time, we're going to see a segment here, PQ, and it's kind of as if they have a really flexible big bungee cord between them as they go around this track. Can you imagine what it looks like? Well, here's a video, and let's see if the video works. It takes a minute to start it, and there we go. and of length of size 1/2, and it's going twice as fast. So I didn't make a good diagram for this. You'll see a good diagram in a minute. But I could make a diagram of the point on the circle represented by e to the it, and then attach to that a wheel a half the size that is going twice as fast, and that would make this green curve here. So this is a wheel on a wheel, and later we're going to have wheels on wheels on wheels, and maybe wheels on wheels on wheels on wheels. We'll see. So I want to think of these integer-scaled exponentials as ingredients to make shapes. These are my ingredients. And when I think about integer-scaled exponentials, I want to call the scaling factors the frequencies, so that this is a frequency 1, e to the it, and this is a frequency 2. Because frequency has that meaning of how fast are you going compared to a basic signal, okay? So now I want to just mention the vocabulary of functions, just in case that needs some help. So when I write f of t equals that expression, then it's because I'm calling that a function because the expression assigns a specific point in the plane, which is a complex number, right? The sum here is a complex number and therefore a point in the plane. It assigns a specific point to every input value of t. There's no ambiguity. So you tell me what t is, there's a specific place where that curve must be. And then I want to use the vocabulary of periodic functions. So this e to the it, because of its relation to the circle, and because of the fact that this 2 is an integer, it's not 2.1 or 2.5, it's an integer, then this has the property that if you wait 2 pi longer, then the whole thing will repeat itself exactly. So that's to say that this function is a superposition of wave functions. Superposition is a fancy name, but all it means is to add this way, and possibly add with scaling. And if you say, why is that going around a circle a wave function, you can just look at that circle on its side, and you'll see a particle that may be going around that circle, but it really is just going up and down. So this does have what I don't know, more conventional people might think of a wave. It's just going up and down. It's a wave function just going up and down. So this is a superposition of waves, and I want to get us involved with what other things can you do with a superposition of waves. Now in the next few slides I'm going to get pretty mathematical, so hold on to your hats here. I'm going to superimpose periodic time rescalings. That's going to give me a set of functions. This is a function space. It's the set of all the expressions you could make by putting integers in for n. Before I had e to the I times 1 times t, and 1 is an integer. And I had a half, and a half is a complex number, and I had e to the I 2t, and 2 is an integer. But this invites us to imagine that you just keep putting in terms like this. You can have as many as you want, and theoretically you can have infinitely many of them. So this is a set of functions that someone can make. I think of it as, the totality of things I can cook with my recipes. I have these ingredients to add, and this is the totality of things that I could create by combining those ingredients. And the question is this the same as the class of periodic functions from the real line into the complex numbers? So I've shown you things that take time and wind it into the complex plane, and they keep coming back on themselves, they're periodic. Are these sums the same as all these functions? So that's a very big question. And can we make the most general shape with a formula like this? So if I have a function that's made from my ingredients, is that enough to make any shape at all? Well, I'm going to show you an animation that is a pretty convincing argument that, yes, you can make anything. And by the way, this is called a Fourier series. So it's just a fancy name. To think about Fourier series, we might issues of whether, gee, if you have infinitely many of those things, does that sum make sense? Infinite sums can be a little tricky. There are issues of convergence. There's all kinds of fancier things to think about. But this really is, we're thinking about Fourier series now. We started with just a circle, and now we're thinking about Fourier series. Beautiful world of mathematics. But watch this video. It's really kind of amazing. Yeah, and in a suitable sense, yes, you can make every shape. The theory is well understood. There are caveats. You can't have functions that jump too much. You can't have functions that kink too much. But yes, you really can make any shape. So here's my convincing evidence. This is an animation showing wheels on wheels on wheels. And what is that making? That is pretty convincingly tracing out the outline of a letter pi. So you can see the big red wheel in the middle. That's just the particle going backward along the unit circle. I call that one e to the minus it. And then it's got these other circles scaled, and they're going at different tempos. And how did the person who made this video, wasn't me, figure out how to do that? There's a very well-developed theory that I consider to be a little beyond the scope of what I want to do today. But I want to tell you that this video was made by a Spaniard named Juan Carlos Ponce Compuzano. And there was a coding challenge by a mathematician named Daniel Schiffman to make sort of the best illustration of wheels on wheels on wheels on wheels on wheels. And this was one of the winners. I really think it's a winner. And isn't it fun for mathematicians to make a pie out of wheels on wheels on wheels? But I have to say that much as I love to talk about wheels on wheels on wheels, the website creator 3Blue 1Brown posted the definitive video about this topic in 2019. So if you really want to know more about how things are made out of the circular superposition of waves, I really recommend that video. It's quite easy to find. Instead, I'd like to tell you about my own work from 1996. My goodness, that's a long time ago now, almost 30 years. I published this article in Mathematics magazine. And I had been doing research in another area of mathematics, and this was the first thing that convinced me that I really wanted to move in the direction of creating mathematical art. So this was a benchmark for me, and I'm very grateful for how things turned out. The image on the screen, that curve that I showed you at the beginning of the talk, that's one of the central images, and we're going to spend a few minutes now talking about it. You could call it a medallion or a rosette. Rosette is a name for an object with central symmetry, meaning that if you put a pin in the center of it and turn it by, how many degrees would that be? I wonder if you can ask yourself that. I'll tell you in a minute. Then the curve falls into coincidence with itself. If I had transparencies and 2 copies of this, I could turn this, and turning it exactly the right amount, it would turn out to be exactly the same, as if I had not turned it at all. So that's what a rosette is. It has a symmetry that is a rotation. So I want to help us understand the symmetry of this particular curve. Now, at the time, I was using software called Derive. It was rather primitive software. And I was designing curves for my students to study. And actually, I was writing things in terms of cosines and sines because I hadn't figured out how convenient it was to use complex notation. And also, my students had not studied complex numbers at that point. But if I'd known how easy it is, I would have convinced them. So think of this as something that I picked at random. You figure you're going to have e to the it because it's right in the middle. And then let's have half of the next thing. And I don't know, I picked 6. And then I turned it by putting in that I. That has the effect of turning this wheel. And I divided it by 3 to make it smaller. And I don't know, minus 14 seemed pretty random to me. So that formula gives this curve. And you look at that and say, I'm looking for the 5. Where is the 5 in that formula? I'm not seeing it. Maybe you're cleverer than I was at need to go through a little something about rotation and complex numbers. So I want to invite you to think about e to the I 2 pi over 5. Let's just focus on that quantity for a second. We said e to the it represented the point on the unit circle that was a fifth of the total way around. 2 pi is all the way around. Let's go a fifth. And if you prefer degrees, 2 pi over 5, 360 degrees over 5, 72 degrees. So that e to the I 2 pi over 5 represents the point on the unit circle that's sort of about here, about 72 degrees. Well, what if I multiply that times just any point at all? The point x plus iy, this represents the generic point in the plane. It's any point whatsoever. Well, I turned the e to the I something into cosines and sines, and I multiplied it all out. Oh my, that's a big expression. But you see that I've got the real part is the cosine of the angle times x minus the sine of the angle times y. And the horizontal component of that point is the sine of the angle plus the cosine of the angle times y. Now it turns out that these are the rotation formulas for points in the plane. So this illustrates that multiplying by e to the I 2 pi over 5 is the same as rotating that point by 72 degrees. And that's a wonderful thing to know. Let's see how that enters into the analysis of the mystery curve. Yeah, so when I multiply by this magic number, that's the same as rotation through a fifth of a turn. In this curve, I said I sort of picked these at random, and what is it about them? It's like, look at this point. My red arrow doesn't quite point in the right place. I mean to draw your attention to this, like, little loop. That little loop. Over here, 2 pi over 5 of the way around, there's a recurrence of that loop. And every 72 degrees, there's a repeat of that. Now, in terms of the vocabulary of the curve here, and oops, I thought I had changed all the thetas to t's, but here's one where a theta crept through. Sorry, it's just another symbol. Anyway, that angle advances by, how much of the way in the time domain is this? That really is a fifth of the way later. So this brings me to the functional equation for symmetry. Let's read this together. Take the function and advance time by a fifth of a period. And that's the same as, that nice equal sign, rotating the curve from where it was before. So you can pick any point on the curve here and advance time by 2 pi over 5, and that's the same as a rotation of that point by a fifth of the way around. So this is the functional equation for symmetry. It explains why this curve has the appearance that it does, and the next thing I want to do is try and help you understand how this is really key to allowing you to make your own beautiful curves, because that's really my goal today, is to convert you all into people who will sit with GeoGebra and make a beautiful curve for yourself, for your students, for your own enjoyment, for the enjoyment of others. So here's the symmetry condition, and I want to think about why the curve that I happen to choose quite by random, why is that curve symmetrical? Well, I'm going to focus just on the e to the I 6t. Did you see in that original curve there was 1/2 multiplied by e to the I 6t? Well, let's do what the functional equation says. It says advance time by 2 pi over 5. That means instead of t, plug in t plus 2 pi over 5. Well, I can distribute here and use the exponential law that you can break up the exponential. A sum in the exponent translates to multiplication of the exponential functions. And I'm going to get e to the I 6t, which is where I was before, times this little leftover piece. 6/5 times 2 pi. I want to write that as 1 times 2 pi plus an extra fifth of 2 pi. this ingredient in the mystery curve sum satisfies this symmetry condition. Therefore, it's a good thing to include if you want to create five-fold rotational symmetry. And the reason this works is because that 6/5 falls apart into 5/5, which is one rotation, plus 1/5, a little bit of an extra rotation, that extra 72 degrees. And the third term works. You might remember that it was e to the minus 14it. Well, negative 14 is 3 times around backwards times 5 plus 1. So the being one more than a multiple of 3 is what makes these things work. Hi! Love to see just a little bit of camera there. I see Bruce. Bruce, glad you're here. Can't hear you because you didn't unmute yourself, but I figure you're saying encouraging words to me. I'll take the encouragement and go on.
Frank, so I would like to introduce to you my best student, Benedicta. She has just dropped in this evening, and now she is enjoying your talk very much.
Oh, Benedicta, I'm so glad you're here. And I see things are in the chat. I haven't been monitoring the chat. I'm going to leave it to others to monitor whether those are questions that I should answer at the end. If you think something is important to interrupt me, then I'll leave it to one of the moderators to do that. Thank you. Okay, so where were we? Let me go back just a second to say that curve at the top of your screen had 1, 6, minus 14, and we went through the just the detail with only the e to the I6t part and showed why when you advance time by 2 pi over 5, that's the same as multiplying times, as rotating through 72 degrees. That's why this curve has the symmetry it does. So the symmetry condition is if you want to make any ingredients whatsoever, you don't have to use 3, you can use however many you wish, and if you pick those a sub n's to be 0, unless you're one more than a multiple of 5, that's what this expression means, n congruent to 1 mod 5. It means you can write the number as a multiple of 5 plus 1. The way 6 is 5 plus 1. The way minus 14 is negative 15 plus 1. That's why this curve has the symmetry it does. It's because I left out all the ingredients except the magical ones that create five-fold rotational symmetry. So now you are in a position to enter an expression like this in GeoGebra, but replace these coefficients by any numbers you wish and find out what your curve looks like. So this is a big idea in my general work, is to restrict to ideas with desired symmetry. And really, GeoGebra is a great way for you to play with finite sums. So I'd like to know later that you have done that. So that's the symmetry condition. And here is just a throwaway aside, is that each of these waves knows how to move forward in time. There's a thing called the linear wave equation that says waves know how to move forward in time. And this is an animation of the mystery curve, as if it's a deformation of the circle, and those little things are springing back and forth. And there's something so aesthetic about the little bounce at the beginning, and it just goes to reverse itself. So anyway, that's kind of my idea of a good time, is that animation. Here's a variation that I said that the condition was you got to be one more than a multiple of 5. What if I'm two more than a multiple of 5? Wonder what that would be like. Well, here I've drawn this curve, and I won't tell you how I found the numbers 0.215 and 0.115. There's an orderly way, but these are the first two terms in the Fourier series for a regular pentagram. So I want to tell about a little episode in my life. In the fall of 19, it was before the pandemic. Mathematicians didn't even know how lucky we were to be all together in person at the Institute for Computational and Experimental Research in Mathematics. They do welcome international visitors. Maybe you might visit Providence, Rhode Island one day. It's a very beautiful city. It's where I had my first job. So looking out across this beautiful New England city, I'm a Californian, but this New England city, especially beautiful. This is what you see from the lecture hall. So I was giving a lecture there, I had a beautiful opportunity. So I was thinking about curves, and I made this curve, and I fattened it up to be not just a curve. Now, can you tell yourself, oh, this one has what fold symmetry? Do you see that it has six-fold symmetry? I think I made this one out of e to the it, and something with e to the I7t, and then maybe some e to the minus 5t, that would work. Anyway, I made this curve, and I saw a demonstration about software that would allow me to fatten this up to make a pipe. So yeah, it's a nice medallion, but when you make it into a pipe, it passes through itself. And I don't know how much I should speed through this, but there's a British architectural program called Rhino, and I got very involved with it, and Grasshopper is a plugin that allows you to do this fantastic plug-and-play programming. So you see here I've typed all of these exponential functions, and I'm not going to go through this in detail, but that is a wheels on wheels on wheels expression with three terms, and I've got one more than n and one more than negative n. So, and n, where is it? Here. There's a feeder up there that feeds in the number 6 to make this six-fold symmetry. And then I just made it a point, and then it made a curve, and I made a pipe around that curve, and then I saw that it passed through itself, and then I decided to use a Fourier series for the z-coordinate, and that's up here, and that just wiggled it up and down. So I made this curve so that it would not pass through itself, and really the mathematics to do this beautiful thing is just the simple stuff that I taught you before. It's all just using e to the it and leveraging it. So I want you to make your own one of these, and then I saw this one and said, that curve could hold hands with a bunch of neighbors, and it could become a grid. And I wiggled them enough so that they linked with each other. And then I was looking at a wallpaper pattern, saying, oh, I've made wallpaper out of these links. And then I realized, you know what some people call wallpaper made out of links? Well, that's chainmail. So here was my first mathematical chainmail. I have printed this in a 3D print, and it really does come apart. And here's another one. So I wrote this as a paper for the Bridges conference. Bridges articles are accessible for free. It pretty much uses the mathematics that I've explained already. So if you'd like to go in that direction, you could figure out how to make your own mathematical chainmail. Who knows, maybe invent a new material made out of these things. So I wanted to just say 2 minutes about my earlier work, because it's after I was doing curves, I went into plane waves. You can imagine the long, big waves in the ocean, not the breaking waves, but the really smooth waves in the deep, far ocean. And I figured out a way to take a photograph and use a formula for two-dimensional waves and make it into a wallpaper pattern like this. So over here, there's a function of the plane that takes values over here. So it's a complex valued function. You plug in a point here, and it tells you which pixel in the photograph to make. And that is I used a formula that I knew would be symmetrical, and it made this wallpaper pattern. So I knew that there should be waves that would make beautiful wallpaper. I can write down the most general formula for a wallpaper function, and then I experimented and found beautiful examples. These are really fun to look at in detail, because the nub of the peach here, it's just, I don't know, it's part of the beauty of the earth for me to see the beauty of the peach reflected in mathematics here. It really, and the color grading of the peach, and the splashing of the water. This is just my idea of seeing the relationship between beauty of mathematics and beauty of the world. So, in a happy thing, a Belgian Belgian signal engineer who had read my book wrote me and said, "Oh yeah, I made octave code to make that." So there is free software that's available to sort of make these. But if you wanted to know more about this, you would want to read my book. It's a little bit of a slog, for it's meant to be understandable by an advanced undergraduate student. So I don't think it's really accessible at the high school level, but maybe, maybe for an advanced high school student. And I'm always glad to hear from people who are trying to read my book. Chapter 3 is an explanation of wheels on wheels on wheels in pretty much the way that I explained it to you today. So here's the latest chapter. Here's a formula, and you look at that and you say, this should not have five-fold rotational symmetry. 20 is a multiple of 5. 79 is one more than a multiple of 5. And 118 is 2 less than a multiple of 5. No way will that have five-fold symmetry. Well, that's the graph of it right there. So these people in Taiwan sent me this figure and said, according to your book, this curve should not have five-fold symmetry, but look at it. What's it doing? Why does it look that way? So, of course, my response was, what? How can this be? Well, we've got an article that's nearing submission called Phantom Symmetry from Wheels on Wheels on Wheels. And just the shortest explanation is that there's no real symmetry, but there's an envelope there. So remember before, we talked about envelopes as visual illusions? This curve creates a visual illusion by sort of touching itself at different points, and that causes this symmetric envelope. I'll close by showing you 2 recent artworks. So this one is a formula that's like the one that the guys from Taiwan sent me, but this one has seemingly 6-fold rotational symmetry, and there's 2 ways to look at it. One is to take this loopy thing with 5-fold rotational symmetry and repeat about 50 copies of it in a very specific way. That makes the blue shape here. Take the gold thing, make like 50 copies of it in exactly the right way, and that makes the blue thing. But the blue thing is visually indistinguishable from the red thing, which is made by a single curve, of which this blue thing is the first 24th of that curve. It looks like it's going nowhere, but by the time it gets done, it makes this red thing here. So that's, I don't know, that's my idea of a good time. My next artwork is called Views of the Olive Wood Bowl. I made a bowl out of this thing. There's a way that these two-dimensional things naturally pop up into 3 space, and you can see that there's loopy curves here, and I won't take too much time to explain, but it's 2 ways of looking at the same thing. And you might contrast, for simplicity, this gold thing at the left and this gold ribbon thing at the right. I'll show you some formulas that go with these. This is a function of 2 variables that makes these things. It's e to the it plus e to the is, plus e to the I times 3t plus 3s. And on the left-hand side, I've made this into a single curve by putting in 29t for the t and 47t for the s. And that makes a very, very loopy curve, and if you look down on it, it's going to look like that. It has an envelope that has 5-fold symmetry. Another way to look at it is, I didn't have that one. Down here in the corner is if you plug in a particular value of s, then you get a thing with 2-fold symmetry here. That's the purple thing here, and you make lots of those. Instead of that, there's a close-up at the top right. That's imagining a closed box. The box opens to reveal this incredibly loopy thing inside, and you can see the envelope here outlined in gold with 5-fold symmetry. So I'm very delighted to be able to make these things. I'm glad that I'm living at a time when the technology is here. We're dancing over it, love it. That allows me to do this, and now I think I'm ready to stop and say that this is now time for you to create something. Because maybe you won't get to creation in Rhino soon, but creation in GeoGebra is where it starts, and that really is available. So thanks for your attention. I'm really grateful to spend this time for you. And I think now it's time for me to think about some of these questions that have been coming up.
Okay, thank you, Prof. Faris, for this inspiring and magnetic session. It was really a celebration of creativity in mathematics. I thank you to our audience. Now it's time for questions and reflection. So if you have any question, you can unmute yourself and then ask Professor Faris. I'm sure he's be ready to answer all of our questions today. And if you're not able to unmute yourself, just type your questions in the chats and we will read it to Prof. Faris on your behalf.
Thank you. I did see a couple of things in the chat. Everything I'm saying can definitely be done in Desmos. I don't use Desmos, so I'm not an expert on how it uses complex numbers, but I know that it can use complex numbers. So for me, GeoGebra, Desmos, they're about the same thing, with GeoGebra being a little bit more easy to use for geometry, and Desmos a little bit more easy to use for calculus. There was a question, will I share the presentation? Well, instead of sharing the slides, I want to share with you a PDF that has a lot of links in it that you can click on to do the GeoGebra files for yourself, because I really think that it should be you experimenting with GeoGebra on your own. And then, of course, these presentations are offered on YouTube, so you can go back and watch, and you can watch it fast, you can fast forward, and see any of the slides that way. What other questions might you have?
Yeah, Professor Frank,
Yes.
my students have to go home and go to sleep, but they would like to they have really been enjoying the videos and pictures and the formulas.
Yay.
Okay, Benedicta,
Grateful to hear.
wave, Benedicta, wave, and Monica, wave.
Yay.
Okay, thank you, Professor Frank. We'll send you more questions over email.
Thank you for staying up
We
to
love you.
do the presentation. Good night. Yeah. Very cute. Well, do others have questions? I know sometimes it's hard to think of what to ask, but I'd be happy to hear from you. I'd be happy to go back anywhere. I know I'm probably at the end of my time. Yeah, I'm amazed that I've been involved with this inquiry for more than 30 years now, and it keeps surprising me that there's always something new. But I hope that your experience with mathematics is like that. That, you learn something, and then a few years later you learn it a little better, and then you learn it a little better, and then somebody asks you a question, and suddenly a whole new door opens. That's really what mathematics is like. We never run out of things to be interested in. I'm approaching retirement age, and I know that even when I'm retired, I will always find interesting things, something new to make, some suggestion. And getting the email from my new friends in Taiwan to say, wait a minute, this curve doesn't have five-fold symmetry, this curve seems to have five-fold symmetry, but your formula said that it shouldn't. That was a gift to me. That was a great gift in my life. So who knows but what someone from Ghana is going to write to me and give me another gift like that. And sometimes I'm in Zoom meetings and I like it when the host says, and now we will have just a moment of awkward silence. While people think what question they may want to ask.
Okay, looks like, do we wait for another 5 minutes if you are still thinking about our questions?
I would like to recommend, Frank, that retirement is a wonderful thing. I have been retired for 4 years, 2 of which I have spent in Ghana, learning what it's like to be a junior high school mathematics teacher. It's an amazing experience. So
I'm so grateful for your experience, and I've had a little window into it, and that really does inspire me.
I'm very glad that you were able to join us tonight, and and get a taste of working with my colleagues here in Ghana.
Yeah, and
So,
I understand that there are sometimes obstructions to sharing video and to speaking up with questions, but I hope that people have benefited from my efforts here today.
I am here to say that the African Institutes of Mathematical Sciences, there are branches in Ghana, Rwanda, Cameroon, South Africa, and Uganda. They welcome visitors from Europe and America, and, well, anywhere. And so, okay, I'm not an official representative, but I'm unofficially inviting you to come in person to Ghana and bring some of your artwork in person.
Very kind, Bruce. I would love to think that I could take you up on that. Nancy Neudauer has been working on me for many years now. She has visited many of the branches of Ames. So.
Oh, okay. So where the process has started. Okay.
Yes, I'm getting now worked on from two fronts, I would say.
Oh, fantastic. Okay, I'm going to let somebody else ask a question, but we'll catch up later.
Okay, looks like there is no questions, but we will send our questions via email to Prof if we think about any other questions that you want to ask. So I'll say thank you to all our audience for joining us today on our 4th episode of the IDM webinar series. We are deeply grateful to Prof. Faris for guiding us through this. It was actually amazing. I'm sure all of us enjoyed it. Okay. Thanks once again, and we look forward to seeing you in future IDM sessions, maybe next month. Thank you, Prof. And thank you, Professor Raymond and Professor Bailey, for joining all of us today. All right. Have a good night in Africa, and those in the United States, have a good afternoon.